Alright, silly people, here's the situation. We're going to be creating a code which is going to um, do some image processing of, we're pretty much just going to be showing how light works whenever you shine it onto a surface, which is defined in data. Um, so the data that we have to do this with is the altitude data from the online resources, which I have up here already uploaded to the runtime. Um, and it follows through this line of reasoning here that we're going to be pretty much calculating an intensity um, between all of the grid points of that data. And to do that, we need to get the derivatives of all of the grid points in that data. So um, let's get started on that. We are going to need NumPy, and we are doing density plots, so I'm going to also go ahead and import matplotlib.pyplot as plt. And so first thing is to load in the data that we have to use. I'm just going to call it W in keeping with the notation of the problem. For the first part of the problem, we're going to be loading in the altitude.txt data. So W is going to be the NumPy load text, just loading in altitude.txt. And so whenever we do that, our first thing that we have to know is how big the data is. I don't actually know a number for that, but we can just have the computer calculate it. So the size of the data that we'll use is n, and it's going to be the length of the array, but only the first column, right? That should be fine because it's a square array. Then we can create a couple of output arrays that I'm just going to call dwdx and dwdy, both of which are going to have the same shape as the input data. So right now they're just going to be empty arrays with size n comma n with the float data type. And so this is also that. Let me also grab the equal sign. Perfect. And so how we're going to calculate the derivatives, though, is the interesting part. And I kind of already did this a couple of videos ago when we were doing the electric field program. But it essentially involves doing off-centered differences using that definition of the derivative on the edges of the grid of input data, but then using centered difference formula on the the points that are not on the edge of the grid data. So what does that actually look like? So dwdx, just to capture like the top row of the data, we're doing 0, comma I, not 0, comma I, comma 0, flipped them. And to do that, this is an off-centered difference. So you will do W indexed 0, or no, I comma 1 minus W indexed I comma 0, and you'll divide it by H. Now what is H? It has to be the spacing in meters in between each of the, each of these grid points. In this case, it's 30,000. So let's just put that in. H equals 30,000, right? So that's that. We can also do the bottom edge of the data with n comma 0. And it's actually going to be n minus 1 comma 0. And that's not even right. It's going to be I comma n minus 1. I'm in a mood today. And that is also going to be an off-centered difference using W indexed I comma n minus 2 minus w comma I comma n minus 1. That's also divided by h. Okay. At this point, we can create another for loop within this for loop. So for j in range, and you just want to have it run from 1 to n minus 2 to calculate dw dx for every other point in the grid data with a centered difference this time. So this time we can use I comma, or w indexed I comma j minus 1 minus w indexed I comma j plus 1 over h. And it's actually over 2h because now this is a centered difference derivative. And I'm just going to make sure I actually did that right and didn't get them flipped. Actually, I did get them flipped. This one should be the plus 1, and this one should be the minus 1. Okay, that looks fine now. So that's how you get the dw dx array. To get the dw dy array, you do much the same thing, except you do j first, so you can get the edge pieces for those. So dw dy indexed I comma, not I this time, but 0 comma j. So the left edge of the data, that is going to be just 1 comma j minus w indexed 0 comma j over h. And then the right edge of the data we'll be indexing n minus 1 comma j and setting that equal to the off-center difference. So w indexed, w indexed n minus 2 comma j minus w indexed n minus 1 comma j over h. Okay, then in here we'll do the for loop over I. So for I in range 1 and minus 2 again, we'll calculate dw dy just of I and j. So every other point, and it's going to be w, not 2, but w, I plus 1 comma j minus w indexed I minus 1 comma j over 2 times h. So that is good there. So to calculate the intensity though, which is what we actually need to do, so this is now getting into part B, we need this formula here. So it involves cosine and sine of phi. We're going to be using phi equals 45 degrees. And I'm just going to hard code it in as phi equals pi over 4 because the numpy versions of cosine and sine take as arguments radians, not degrees, so just that there. And then after that, we'll get into making a output array for the intensity. So this is going to be another empty array of size n comma n with the float data type, and we're going to be running for I in range n minus 1 and for j in range n minus 1. You just calculate I comma j using the formula above, which was minus sign, and then in parentheses it was cosine of phi times the x derivative, so this is going to be dw dx indexed I comma j, and then plus the sine of phi times dw dy indexed I comma j, right? And then it's all divided by a square root of the x derivative squared, so dw dx I comma j squared plus dw dy I comma j squared plus 1. That plus 1 is there. I'm not sure why that plus 1 is there, but it is nice because we won't ever end up dividing by 0, I don't think. And after that, you can do your density plot. So you'll do plt.mshow using I as your map. For this problem, it kind of suggests that we use the gray scale for the color map. And I found that for the vmin and vmax arguments, that if you put in 5e minus 3, and that's actually vmax there, and 5 vmin equals minus 5e minus 3, then you can get a color map which really pops. And you can really see all the mountain ranges and things of what is just the western hemisphere of the world. The problem says that it's a relief map of the world, but I'm only seeing North America and South America here. Kind of concerning, but whatever. And yeah, you can pretty clearly see the mountain ranges. These are the Rockies here. There's just the tectonic plates of the ocean. You can clearly see the plate of South America. This is a big mountain range that goes down the southern edge and getting into Chile. So yeah, pretty cool little density map there. Part C just tells you to use a different data file called stm.txt, which is it's a microscopic image of silicon, and so we don't have to change much of the code. We just have to make sure that we uploaded the STM data file to load in, and because of the way that I wrote it, the only thing we have to change really is load in that particular data file and also use a different value of h, which is 2.5 for the silicon. So give that a run, and then oh, I did 2.5 instead of 2.5. That's just a typo. Okay, so that will give you, once it's done running. Okay, so yeah, you can see the structure of silicon as you would see it if you were actually looking at it with visible light, which is pretty nice, if I do say so. All right.